derivatives of exponential functions. So far we have considered differentiation of one type of function. All functions we have met so far are of the form y equals ax to the power n, where the a and the n are constants. The differential of this type of function, as we've seen, is that dy dx is equal to nax to the n minus 1. Different families of functions differentiate according to different patterns. Here we're going to look at exponential functions, starting with the basic function f of x is equal to b to the power x. So let's look at a graph of that function. If b is greater than 1, then it will look like this. Let's take a point here and another point over here. And what we're going to do is a limiting chord argument again. So this point here, if the x-coordinate is x, the y-coordinate is b to the power x. And if this point here has x-coordinate x plus h, then the y-coordinate is b to the x plus h. We're just substituting x plus h into the function. So, again, we'll do a rise over run. And, of course, this is a right-angled triangle that we've formed here. This distance is h, that's the difference between the x-coordinates. And this one here is b to the x plus h, take away b to the x. From what we've learned before, we can say that f dashed x is the limit as h tends to 0 of b to the x plus h minus b to the x, all divided by h. So let's work with this. We know from our index laws that we can split this to b to the x, b to the h, minus b to the x, and then we could factorize that. So we can take out the common factor of b to the x and give us b to the h minus 1 over h. Now note that the b to the x here doesn't have an h, so it's not really affected by this limit because the limit changes h to 0. And that means that we can actually just take that completely outside. B to the x times the limit as h tends to 0 of b to the h take away 1 over h. Now, if we consider f dashed of 0, so this is f dashed of x, so we're replacing x with 0. So if we consider f dashed of 0, which is this, that's the limit as h tends to 0 of b to the h take away 1 over h. So you'll notice here that f dash 0 is the same as what we have here. So we can write f dashed x is equal to b to the x multiplied by f dashed of 0. Now that's a general case. What we're going to do is look at a particular case where b is equal to e. E is a special number. It's an irrational number like pi. Now, in the case where b is equal to e, so what we have is e just here, e to the h take away 1 divided by h. In that special case, we can show that f dashed of 0 is equal to 1. That's why I say without too much analysis. I'm just telling you that's the case, but we can do that analysis if we really need to. Now, e is approximately this, but as I say, it's an irrational number like pi. And because f dashed of 0 is 1, f dashed x will just be e to the x multiplied by 1. So we have this special feature that if y is equal to e to the x, then dy dx is e to the x. So we have a function which differentiates to itself.